Okay, welcome back. We are starting the fourth course of the school by Sourav Chatterjee, who is an astrophysicist at TIFR. And he's also one of the really most active scientists in the field of identifying how to create merging black holes in the universe, for example, or understanding how nature creates merging black holes in the universe. And he was part of a group which, even before the detection of gravitational waves, predicted pretty accurately the possible, a very new channel, well, not a very prominent channel for creating merging black holes. And it seems to be one of the most promising channels for creating astrophysical black holes. So we are very lucky to have Sourav teaching us how nature creates merging black holes.
Thanks, Ajith. It's great to be here. Thanks for the hospitality. You can all hear me, right? All right, good. The topic of this course is, well, the broader topic is how to make merging binary black holes. As you will see, that it's not easy. But universe is vast, it can create all kinds of crazy things. In particular, I will talk about the dynamical production channel, because I think it's very well understood. There are not many uncertainties, and it's a lot of fun physics that goes on, okay? Let me start by showing you a movie. So today's lecture is more about what I will cover, what to look forward to, and then give you the basic concepts, what really matters in creating these binary black holes. And then over time, we will learn more and more the formalism and so on, okay? But let's start with a movie. What you are seeing here is, I think, all stars and black holes in the core of a globular cluster. And just to make it pretty, in the background, there is a Milky Way galaxy picture that is static. So we are using that just to show, so that you can see the black holes through lensing, gravitational lensing, right? So what you are seeing here is velocity dispersion. So stars are speeding up, okay, from the beginning. This is because this cluster is going to a so-called core collapse. You will learn all about core collapse this week. And then we are zooming in, and at some point, you will see that, so a lot of crazy things are going on, right? So you see binaries getting created, stars getting flung out. Some of these stars are actually getting ejected, but you don't see it in that movie. There are all kinds of black holes. Some black holes come in pairs, but pairs don't last for very long. They get broken all the time. New pairs are created. And then, at some point, you create black hole binaries that are so dominant that nothing else can break it. At that point, so that's the zoom in. So you have created a binary black hole that is tight enough that nothing else is breaking it. And then it will keep oscillating like this until, through gravitational wave mergers, they merge. Okay? So that's the main process that we're going to talk about this week. Okay? So essentially, in very dynamical systems, you collect all black holes from everywhere in that system in a small, dense part, and then they interact with each other like crazy and create all kinds of objects, okay? So just to give you some early warning of what we are going to do, so today is all about what are the astrophysical origins. It will be very pedagogic. I will show you pictures and movies. Tomorrow, we will start going deeper into the formalism of how to solve a gravitational n-body problem. It turns out that it's a very unique problem. So as you have seen many different types of large N systems, like ideal gas or whatnot. But gravity is a unique force, and that creates all kinds of unique features for a gravitational n-body problems. We'll talk about that, hopefully, in lecture 2. And then we will go deeper and deeper into what is relaxation, what are the time scale, how to differentiate between different classes of gravitational n-body problems, and so on. And then, hopefully, the last lecture will be where the cutting edge is, what we know, and what are the main questions where you as students or postdocs or young researchers can go ahead and contribute in the next, say, 5 years, 10 years, okay? So, although I will focus on the dynamical formation, but that's not the only way you can form merging binary black holes. So let's just review that a little bit. Oh, before that, we all know that there are these gravitational wave detectors. This is to motivate you about astrophysics of gravitational waves. So in India, for example, there are leading groups who are very much involved in gravitational waves, their detections, data analysis, how to extract properties, etc. Not many strong groups exist that tries to go from the other direction. Let's say that you have detected gravitational waves, you have the properties of what you have detected, but what does it imply in terms of what kind of astrophysical systems that have created them? So that's where you, as young researchers, can go ahead and contribute a lot, okay, in India. So anyway, so there are 3 operational detectors now, and we have detected gravitational waves of several sources. This is the consensus, sorry, this is the, this is now blocking it. Anyway, 6 detections for binary black holes, 1 detection for binary neutron stars. There are other black holes detected as well. These are from X-ray emissions for accreting binary black holes. Neutron stars are also mostly in accreting systems. There are some pulsars as well. So this is all we know about dead bodies of massive stars. Okay? And based on the gravitational wave merger detections so far, these are the rates that the LIGO collaboration gives out. So there are 2 different merger rates. So this is per volume, per year. 2 different levels of merger rates, and that depends somewhat on what is the mass distribution for black holes inherently. So we don't really know that, because we don't really know, we haven't really detected a large number of black holes, and whatever we have detected are modified by various selection biases. So, and from first principle in theory, there is no clear way yet to exactly know, given some metallicity and zero-edge main sequence mass, what is the black hole mass should be. Okay? So there are these uncertainties. These are the rates. For binary neutron stars, the rate is much higher. It remains to be seen whether which direction this goes in. There are large error bars. There are several problems in making, from astrophysics, making binary neutron star rates to be as high. Okay? But no matter how these numbers pan out over the years, one thing is sure, that they merge fairly frequently. That can be detected by these gravitational wave detectors. That, I just picked them up from about 2017. So there is, if you assume a log normal type distribution for mass and the same distribution for the secondary, then rates go down a little bit. So this is all about what the inherent black hole mass function is and how exactly the mass ratio in black hole systems work. Well, these are young times. Right? Anyway, so one thing is for sure that in the next 5 years, LIGO is going to detect a large number of these mergers, like black holes or neutron stars. The mass function is very narrow. It doesn't depend on the masses. So in the next 5 years, let's say, we will probably have detected hundreds of these mergers. And then it will go exactly the exoplanet's way. So long time ago, in 1995, 6, it was cool to write papers saying we have detected an exoplanet. And there, nature was flooded with papers or detected an exoplanet, detected the first of this, detected the first of that. This is that same phase in gravitational waves. 5 or 10 years from now, it will not remain that phase. The major questions will be, we have detected these hundreds or possibly thousands of these systems, and this is the distribution of their properties. What can this tell us about astrophysics or cosmology, gravity theory? So that's what the frontier is going to be when you will be in the job market. Okay? So be interested. And actually, these rates are going to be really realized. So these are intrinsic rates. But whatever the intrinsic rate is not the detection rate. But it looks like there will be several other detectors in addition to the operational ones, including one in India. A lot of people, a lot of you are working actively or involved actively in this experiment. So the question really is, what's the astrophysics? So let's talk about how merging binary black holes form. So when I say merging, that means the black hole separation must be small enough so that gravitational wave radiation rate is high, and they radiate enough energy to merge within, say, Hubble time. Okay? And that turns out to be quite challenging, actually. And you will do one toy problem about why. It's very simple, actually. So even before going to merging binary black holes, let's, for a moment, appreciate how rare black holes are. Okay? So if you look at a mass function, so we call it stellar initial mass function, or IMF. It can be approximated by a power law or a series of broken power laws. There are several different people at different times have given power law expressions for what is the mass distribution during star formation. It is observational, it's completely empirical. The motivation for a power law is actually theoretically guided because star formation depends on a large number of seemingly independent processes that work on various different timescales. So you expect, so a natural form of function is a power law when it's a result of a large number of independent events. So that's why it should be a power law. In addition to that, astrophysicists love power laws. But yeah, this is totally empirical. What I want to, so if you haven't realized this yet, roughly this part is the part that creates black holes. So it's very tiny area of the whole parameter space. And if you write down the number of stars per mass n as some power law of the mass, then the usually used power law indices are pretty steep. Okay? So you can very easily find out for some n stars formed, how many black holes you can form. So this is black holes, period. Not even binary black hole, not even merging binary. Okay? So it's typically 10 to the minus 3 times n. It is local universe. It is assumed to be universal. There are probably hundreds of papers saying that, oh, we have seen variations, but then some other thousands of papers that says, oh, these variations may be statistical. Yeah. Unless you find something that totally says that it's different. So you realize that it's so general, this definition, that it's very hard to qualitatively change it. Maybe you can say that, oh, this is not 2.3, this is 2.1. But saying that this is not power law, or this is not a reducing thing, that is saying something. Nature doesn't work that way. I think the highest known mass, or theoretically expected mass, is somewhere near 200. Main sequence stars. Yes. You see light, and then you, yes. So you see light, and then you try to estimate what the metallicity is, and then you run stellar models. From that, it gives you some mass. That's actually a very good point. It's for very high mass stars, it's very hard to exactly measure what the mass is, because they lose mass very quickly through strong winds, as well as they die within a few million years. So the number of high mass stars, well, they form in low numbers, they die very quickly, they change mass very quickly. So catching them and finding exactly what their age and, as a result, mass is very hard. But in general, you can at least say, oh, this thing is 100 or more, plus minus 20 solar mass. So that's the nature of error bars. And typically, the nature of error bars for age is 3 plus minus 1 million years.
Excuse me, sir. So is the magenta line the observed thing? Observed from observations?
No, so all of them are from observations.
Okay.
These are for different people.
Okay, so I see a peak a little greater than 0.1, and also it deviates from a power law around 1 solar mass. So are there any physical reasons associated with this?
No.
Okay, it's just the observation.
It's really, someone thought that this fits their data better. So this is low in number, and this is hard to observe because they're faint. Yeah. So if you look at the masses, so that's in the brown dwarf region. Yes, but whenever So this goes to some of the gravitational wave merger rates as well. So when you observe something and apply selection effects on it, it's more believable than when you don't observe something and say, because of selection effects, I'm not observing something. I cannot hear. Yeah. Right. So, no. This is not about whether there is a brown dwarf desert or not, whether planet mass function goes smoothly to stellar mass function. This is not about that. The point is, only this part creates black holes. Okay? And since this is a course, I will give you quizzes. You don't have to do it now. So I gave you what the power law form is, index. So you can very easily find out how many black holes in stars create. And then the question is whether the total mass is dominated by the massive guys or the low mass guys. Okay. And then this is the stellar systems, whatever you find. And another type of systems that's also abundant in nature, that has a very different mass function. Okay, so if you do these two, it will become more clear what I mean by very different type of mass function. Okay? That part only adds to the error bars. That part only says, okay, given some observed luminosity, what is the mass? That doesn't really affect anything. Right. So the deuterium burning limit is the theoretical limit for which you call something a star or not. Okay? But that's somewhere near 1/12 of one solar mass. The other question that Tejasvi was asking is whether the stellar mass function goes smoothly to the planetary mass function. That is an open question. I don't believe it can, especially after Kepler, but you can always be creative. Okay? So the easiest, or not easiest, the most straightforward way you can think of creating merging binary black holes is by starting with two very high mass stars. Okay? So the kind of things you have to be careful about is the more the mass, the bigger the radius. So they have to be at least separated more than the sum of their radii. Actually, it's much bigger they will have to because of tidal forces. So through tides, they might, the orbit might decay and they might merge while they are in the main sequence. So if you take high mass stars and merge them in the main sequence, or any time before they both become black holes, you have wasted two high mass stars in LIGO sense, okay? So this is just a cartoon that Belchinski et al. In 2016 created. So, but this shows the point. So at each stage, you will see two stars and what they are doing, what their evolutionary stage is, what their masses are. So this cartoon was particular for the first detection, 1509-14. But the basic story is the same throughout binary black holes, binary neutron stars, and whatnot. Only the details of masses and separations change. And then this one is showing you what's the separation between the two stars. Okay? So he's saying that it needs to be at least a few thousand times the solar radius. This is because both these stars are pretty big. They are tidally active if they come very close to each other. And then one of the stars become a giant and starts Roshlov overflow. And through Roshlov overflow, if you assume some kind of mass conservation, how much mass is getting actually accreted onto the star, how much is leaving the system, through all these details, your separation changes somewhat. But at this stage, at least in this case, it didn't change much. Yes, the eccentricity becomes 0 because of very strong tides. And then it becomes some other type of star. This is carbon helium burning star. And it keeps Roshlov overflowing. And at this stage, due to all these details of the mass transfer, the separation started becoming bigger. Okay? And one of the details is, see how this was mass transfer from a bigger object to a smaller, or more massive object to a low mass object. You can convince yourself, it's very easy to do the calculation in a strictly conservative system, strictly conservative mass transfer case. You can show that if it goes from a high mass star to a low mass star, the orbit shrinks. The opposite is, if it goes from a low mass star to a high mass star, then the orbit expands. That's primarily what expands this orbit at this stage. So it has lost or transferred enough mass to this main sequence star. Now it is a low mass star, then this one, and the orbit expands. And then this becomes a helium star. So all this hydrogen envelope either gets dumped onto this main sequence star or gets ejected. Mostly ejected because see, the mass of the main sequence star didn't really change much. So anyway, now you have a helium star and a main sequence star, and there is a lot of mass loss. So you can take a look at the total mass on this line to that line. And if you lose mass, then the orbit expands, right? It's not as bound anymore. The orbit expanded. Now it lost even more mass. It became a black hole. In principle, it could have lost even more mass. This is a so-called direct black collapse, where not a lot of ejecta leaves the star through supernova. Okay? So you get a black hole, and it expanded even more. Now the magic starts. Okay? Without this magic, in isolation, there is no way to create marching binary black holes, marching through gravitational wave radiation, binary black holes, or neutron stars, or pretty much anything. So what happens at this stage is this main sequence star now becomes a giant, and it tries to accrete onto the black hole, but due to the details of the rate of mass loss and the rate of what the black hole can accept, remember black holes have very tiny area for accretion to happen. Not a lot of mass goes and falls into the black hole. This mass kind of engulfs both stars and creates a phase called common envelope, because it's a common envelope. So essentially, two stars are moving in a very dissipative environment full of gas, and that dramatically shrinks the orbit. So all of the orbital energy goes to, through friction and drag, goes to thermal energy to this gaseous envelope. I'm not really sure, but I think it's more dense in the plane and not as dense outside. But I'm not sure. What? This is the eccentricity. Did you ask eccentricity or density? Mass loss from the star, yes. So it tries to, it can be both. No, it's, so winds at this kind of stage, I think, is not strong enough to create a common envelope. I think it's Roche-Loeb overflow. It tries to do Roche-Loeb overflow, but then it cannot. And also wind is spherically symmetric, so the amount that goes from this point to that point is very small. So it's very hard to play with that tiny mass. That's a black hole. No, it really depends on the density. So you can have a very high mass thing, but very low density, so it has a big volume. So the differential gravitational force at its edge can be higher from the other star than its own center. So mass is not the main thing, density is. No, he is asking, since this is the more massive thing, why isn't this star is Roche-Loeb overflowing to that star? And the reason is this became very low density because it became giant first. Because this is high mass, it evolved faster. This one, it's all drag. All the energy, angular momentum goes to the envelope. And that's where all the uncertainty comes in. So there are two main parameters. So we don't really know the exact properties of common envelope. There are two parameters that people use to make some sense of it. One is the viscosity parameter, or related to the viscosity parameter. So that is how easy it is to take energy and give it to the gas molecules around it, and then how quickly it disperses to the envelope. That's determined by this alpha, or viscosity parameter. And then the other parameter is called lambda. That is coupling of the energy in the orbital the orbital energy and angular momentum getting coupled to the gas energy and angular momentum. Okay? So in principle, it could be a very inefficient process, and essentially any energy emitted by shrinking of the orbit may be radiated away very quickly. It could have happened. In that case, lambda would be very small. So just by playing with alpha and lambda, you can control how quickly this comes, how close, before this envelope is ejected away. Because if you keep hitting the envelope, at some point it will be blown away, right? There sure is, but it's typically not expected to be strong enough to influence anything. Can you say that again? This one? Yeah. This will not become a black hole. So you have to start with at least 2020. Okay. Common envelopes can work for anything that becomes, I think, a carbon-helium burning star at any point. So you have a helium star inside, and you have a lot of hydrogen outside. There can, in very compact systems, you can also have a helium giant. So now you are starting to burn oxygen, neon, that cycle, CNO cycle. And then you can have a helium shell, and if something is very close to it, it can create a common envelope for that. But those are very rare. So essentially, so if you take a one solar mass star, yes, it will evolve within a Hubble time. So in principle, it can happen. There are actually cataclysmic variables and systems that are so two stars that are touching each other, and all you see is kind of a dumbbell shape that's rotating, and you can detect them because the total brightness from them are changing. So these kind of systems are, this kind of evolution is not unique to high mass stars and for black holes.
Sir, when the black hole is formed, the corresponding main sequence stars is accreting matter, and its mass increases to 84.9, something like that. And the next step, it decreases to 84.7. Is it because of the viscous drag or frictional force, what you're talking about?
So just because a star is losing mass through its Roche-Low doesn't necessarily mean that it will go to the other star. Right? It can just leave both of the system. Right? So that's what's happening. Stars lose mass all the time through winds. This is a particular case of evolution.
But it has already got 84.9 solar mass, and in the next step, it means it has already accreted that amount of mass.
Right. So
from the next step, it goes down
from here to here, it's mostly wind.
Right.
From here to here, its wind mass loss is less compared to accretion mass gain. Okay.
Okay.
And then combine the two.
Okay. And another question is like, this common envelope, is it some sort of an equipotential surface? This common envelope thing?
Roche-Low overflow definitely is. It might be, it should. It's probably the outer equipotential surface that includes both of the L1, L2 points. That's an interesting question. I am not sure, but it should be.
Okay.
Right. So it's hydrostatic equilibrium in a self-gravitating system. With some radiation physics thrown in, because both of the stars are radiating and it's probably accreting a little bit. So you see that we don't know how exactly this works, not because we are lazy, it's a very hard problem. It could be an extra-binary. In fact, some people say that all the ultra-compact extra-binaries are coming from this channel. And some other people say no, some of them probably comes from collisions. Okay, so now we have a black hole and a helium star, and we have magically shrunk the orbit roughly 3 orders of magnitude. So now we are in business. Well, this is a particular system. Yes, if you do population synthesis, you can have combinations of alpha and lambda that will explain the period distribution. And then this becomes a black hole, loses some mass, this makes the separation slightly bigger, and then after some time, so that's the time, in million years, they merge and become a LIGO source, 150914 to be exact, okay? And the main part is, this is where the magic is. Without this, you cannot have merging binary black holes. You can definitely have binary black holes, but not merging. They will never merge. Yes. Catching two high mass stars in the act is probabilistically very small. Finding two very massive stars is very unlikely. You lost some mass. So it was a helium star. From that, it did a supernova, whatever puny. So the orbit must expand. There is no star around this black hole now. For this one. From here to here. So in isolation, the densities are so small that you can imagine that this is truly isolated. There is nothing really left. And this shrinking of orbit by roughly 3 orders of magnitude will definitely blow away this gas cocoon. If it doesn't blow away, then in principle, you could have this thing forming a black hole inside the cocoon. And then if you demand that it's a direct collapse, so no supernova, no energy emitted, etc., then in principle, you can save the cocoon. And indeed, in principle, you could have black hole mergers in a cocoon. And there are some papers that pointed that out. Because 150914, I think, had some claimed Chandra EM counterpart. For me, yes, sorry. Okay. That's what you need to do in isolation. Yes, everything, these are extremely damped systems, no eccentricity expected. Eccentricity is very hard to find. And eccentricities so far are undetectable. And also, even if you start with a very high eccentricity, eccentricities decay as they start merging. And LIGO, remember, catches the last part, last hurrah. So having serious eccentricity at that point often is tough. Okay. Yes. Yes. So this is a fun problem. It's considered two main sequence stars in a binary. You can assume some high mass. You can assume some black hole mass. And check what, so the only thing you need to remember is they must be more separated than their radii. Okay? And then no mass transfer, no tide, you don't have to do any kind of complicated analysis. You just reduce their masses to become black holes and see how big the orbit is. and calculate what is the merger time from that orbital separation. And I think you will find that they will never merge. Okay. So there is another really cool variation of the isolation merging binary black holes. Okay. Oh, before I go into that, any other questions? So that was the most straightforward thing that you can think of. So you start with two very massive stars, both become black holes. Somehow the separation is small enough that they will merge. No. There is almost zero direct evidence of anything regarding black holes. Apart from the LIGO detections, remember that every black hole we have ever seen are black hole candidates. Because we're not, well, no, the supermassive black hole at the center of the galaxy, that is not a candidate because we have measured the mass. There is a mass measurement. If you don't have the mass, if mass is model dependent, it's a candidate, strictly speaking. No, this is assuming GR for ISCO, and then as you finding what the frequency must be, right? So this is model dependent. No, it's extra luminosity and variability. Super Eddington luminosity and their variability makes them black holes. That's how. No, all you see is something that's accreting, and then you can, in some cases, you can go and do radial velocity for that. So once you have a minimum mass, then you have. It's a black hole. Right, but you cannot do it for all of them. They are pretty far, and oftentimes, I think in the plane, so there are some crowding issues. I'll actually have to check how many of them have radial velocity measurement. Okay, so the motivation for this channel actually existed beforehand, but it kind of resurfaced because 150914 was so massive. So the question was, how do you make such massive black holes? So just to give you, if you don't know, so 150914 was roughly 3030, okay, pre-merger mass. The most massive stellar black hole known before that from X-rays was roughly 10, okay? So that's a threefold jump. So this idea is actually pretty neat. So the idea is so a normal evolution of a massive star is you have a star, then you start burning hydrogen and start creating helium at the core. Then hydrogen envelope starts expanding, and there is a lot of hydrogen that you don't burn. So typically in a sun-like star, you burn roughly 10% of its total hydrogen. Okay? So all of this hydrogen then leaves either through slow overflow or through some kind of supernova. And then if the helium core is massive enough, then you can also burn helium and keep going to the higher atomic weight burning chains. But the question is, what if you could keep bringing hydrogen into the center? So the reason why normally you cannot bring hydrogen into the center is because of the entropy barrier. So once you have created a higher atomic weight nucleus, it sinks to the center, and you have to do work for a lower atomic weight thing to replace that and enter. So if you do the hydrostatic equilibrium across the star, you can write down entropies, and you will see that to take a gas parcel from here to there, you need to spend energy. So it never happens. Can anyone tell me what else could you do to do the mixing? So I have already told you that normally it doesn't happen. Convection. Convection won't work because the entropic barrier is very high. Yes, you can mechanically do it. You can make the star spin so hard that these things start mixing. So the centrifugal mixing energy or whatever is so high that it can break the isotope, the barrier. Yes, it's so when you say definitely can, I expect that you have done the problem and you have shown. What you are actually saying is, why can't it do it? The answer would be, write down the equations and try to do it. The isotope, the barrier is very high. So in fact, a lot of work has been done for this kind of problems, especially for stars colliding with other stars. Okay? So, I mean, we know empirically what the mass and luminosity relationships are for main sequence and how stars evolve just from observations. So for doing any of this, we didn't really have to know what is really happening inside. But if you want to understand how a star behaves after two stars collide, you need to know how the reassembly is done once two stars merge to one, okay? And it has been shown that all you need to do is find out the entropy for each gas parcel after merger and just sort by entropy, and that creates the shells. Okay? So you can write down these entropy equations and find out that this doesn't happen normally. But if you can somehow spin the star very rapidly, in principle, you can do it. Sorry. Next slide. Yes. Car is a black hole. Yes. Remember, you also have convection. So you can have mixing along the plane, and then you can have the ADs that mixes the whole star. So the idea is basically, this thing never loses any, never wastes any hydrogen. So at the center, it's always hydrogen and helium mixture. And since it's all well mixed and homogeneous mixture, there is no core and envelope separation. So the whole star slowly shrinks and shrinks and starts gaining molecular atomic weight. And it becomes helium-rich, it becomes a helium star without losing any mass. And then once it has spent all possible channels of creating energy, it collapses and becomes a black hole. No mass is lost, no supernova. Yes. Well, I will tell you where this spin is coming from, because typically main sequence stars are not rapidly spinning because of magnetic braking. Yes, this requires very high spin. Yeah. Unless you can eject some tiny amount of mass and shed all the spin. So the way you can have a star that can keep spinning is by putting a companion very near that star. So imagine that you have another very massive star, fairly close. There is no assumption about magnetic field. People who did these models said, don't know. Typically in astrophysics, as you grow older and become more cynical, you will find out that whenever you cannot explain something, only then you say, okay, maybe magnetic field. When you can explain something, you say, oh, no, who cares about magnetic field? Anyway, so you have two very massive stars that are very close to each other, okay? And they are tidally locked. So this is the Earth-Moon system type thing. So what that means is each star is spinning at the orbital speed. Right? Now, if the orbital speed is sufficiently high to break the entropy barrier, then you can have mixing in both stars. Both stars go through this chemically homogeneous evolution, create very massive black holes, and since no one ever became a giant, no one lost any significant mass, the orbit never expanded, so they can merge within a whole time. And the parameter space of interest where this can actually work is very restrictive. So you need very high mass stars, you need sufficiently low orbital periods. So this is orbital period, this is companion mass. I think the primary mass is fixed to something 30-ish, 1509, 14 like. This would be normal evolution. This, if you go too close, there will be Roshlov overflow, just in the main sequence. This is a tiny parameter space where this might work. What is interesting to note that this channel will never give you black hole mergers that are not massive. So for example, the 1010 solar mass black hole merger, it will be almost impossible to explain that through this chemically homogeneous channel. So you need tides to be very effective for locking. So if you, how effective the tide is depends on how big and what's the AD time scale, and that becomes, things don't really work out. True. There is so much uncertainty in what actually is the star formation rate that I think it's impossible. No, no, no. This is tidal locking because they are too close, and these are extended objects. This is the same tide in the sea on Earth. You have an extended object that can move around easily, like water. It's the same tide. Anything else? Okay. Now, let's talk about some dynamical channels. So these were all with two stars evolving in their merry ways, and in some cases creating matching binary loss. So the easiest system actually is a triple. So you can imagine that you have formed a black hole binary. It doesn't have to be very compact. But then let's imagine that this binary black hole is actually, the whole thing is actually bound to the galactic center, for example. Then there will be Kozai-Lidov oscillations. If you have never seen that, this is how it kind of looks like, depending on the initial eccentricities and inclination. So what I'm showing here, so ignore time, that is a function of the periods of the black hole binary and the binary tertiary orbits, and their masses and their initial eccentricities and inclinations. So a lot of things goes into the time scale. So ignore time. What you want to notice is this 1 minus eccentricity term. So the smaller it is, the more eccentric it is. And you can see that this is how the evolution goes. Okay? So the point is, at times, so this is all about angular momentum exchange between this binary and that binary. And since this binary is much more compact, the angular momentum content in this binary is small compared to outer binary. So any small change in the outer binary can do a large change in the inner binary. The constraint, whether or not this kind of evolution happens, depends on the ratio of the same separations. So how big this is compared to how big that is, and the mass ratios. No, all masses. Smaller one. So you are not trying to merge this with that. You're trying to merge this with that. And the problem with that, in absence to this, is their separation is too big. So, but if they are quasi-active, then although the same major axis is very big, you can have arbitrarily high eccentricities such that at pericenter, you release a burst of gravitational waves. And that essentially is so high that the orbit becomes more bound. And just by that way, repeatedly, you can shrink the orbit and merge them. So now let's make it an n-body system.
Can we just go to the previous slide? So this scale mechanism is essentially based on, I mean, the calculations are done using secular approximation, right? So what happens if the secular approximation is not considered?
When it is not secular.
Yeah, non-secular, does the eccentricity behavior shows these same cyclic things, cyclic features? Or?
Okay. Let me give you a long answer, because I think this is actually very important for all of us. So, by definition, Secular means that where exactly the object is in its orbit doesn't matter. So this is sufficiently slow process for which an object in orbit essentially is like a ring. Okay? So when this kind of approximation is okay, so that means whenever the effects of something is acting on a much, much longer time scale than the orbital time scale, then you can do some kind of, it's similar to mean field. So essentially you distribute the mass of the object throughout the orbit, make it a ring, and the other thing also becomes a ring, and essentially you are solving the, so energy typically is not exchanged, because then you are actually changing the orbit and orbital timescale. All you are doing is redistributing energy and angular momentum between the two rings. Okay? The way this can break is if something else happens at a much faster time scale, where it actually matters where each object is in its orbit, then it's not secular. So that is dynamical, right?
So another
Let's
question,
talk
like
about dynamical systems.
the time scale. So this effect will be neutralized by the radiation effect, GR, gravitational radiation effect?
No,
It will try to oppose and circularize the orbit, no?
yes, but then it will happen again.
Yeah, so there will be a time scale over which this gravitational radiation effect will dominate over this scale mechanism.
Right.
So does that depend on the mass of the inner binary, this GR radiation effect?
Yes, mass and separation. So you cannot really do a secular problem too larger. All I'm trying to say here is through secular, even with large semi-major axis, in principle you can get very small pericenter approaches. And when that happens, you can start gravitational wave radiation. And then, indeed, if you want to do this problem correctly, then you have to do proper AR chain integration with gravitational wave effects. And actually, I stole this paper from this Antonini et al. 2016 paper. This figure was not shown there as an illustration of Kozai-Lidov effect. This was an illustration of why you need to do the hard air chain integration, and secular equations doesn't work in systems like this. So the blue lines are what you would think the evolution is for up to octuple order secular equations. The black one is a gravitational waves, AR chain, like all bells and whistles, very good integrator. And as you can see, that the evolutions are very different. Okay, any other questions? Now, let's talk about dynamical channels. So this is not secular, evolution is chaotic. Things are happening fast on orbital timescales. Stars interacting with other stars rapidly, and they are coming close to each other. Okay? Let me show you a movie. So this was not using black holes, but it doesn't matter. Okay? So all you are seeing is a binary comes in, a single star goes in, they start interacting with each other, and they just keep coming back at each other. And the velocity of importance for the thing that's coming towards the binary, or the relative velocity at infinity, let's say, is the velocity at which the total energy of the system becomes zero. It's called the critical velocity. Okay? Another important velocity is the orbital velocity of the binary. So depending on these two velocities and what is the velocity of the relative velocity at infinity, you can have wide ranges of final outcomes after these kind of events. So you might think that this is a particularly dramatic case. It's actually not. These kind of events happen all the time in dense environments. There are two things that are actually hard to notice on screen. So when the binary came in, it was like this. I can see up close, the dotted lines are, it was big. When it went out, it shrunk a little. So this is a well-known result in dynamical simulations. If a binary is hard means the energy of the star that is coming in, star or binary, is not sufficient to break this binary. That means it's hard. Okay. It's a jargon, but I will be probably using this jargon many times. So if a binary is hard, then through repeated scattering encounters, it becomes harder. That means it shrinks. Okay? So you need even more energy to break that binary. Yes. 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 In a n-body system, so this was a 3-body encounter. In an n-body system, hardness is statistically defined by the velocity dispersion. Okay. So you can imagine, so remember the main problem to create merging binary black holes is how to take two black holes and make their orbits compact enough for them to merge within Hubble time. So in principle, if you can have binary black holes where these kinds of interactions are happening frequently enough, then you can take two binary black holes that are sufficiently far apart at formation, but through these repeated hardening encounters, you can make their orbits shrink to a point where the merger timescale is short enough. So the things that you need are, okay, so, sorry, I went ahead of me. So these are chaotic orbits, you have seen it. So if you just simply change the seed of the problem, use the same exact everything, the outcome may be completely different. If you use exact same thing on this machine and run the exact same thing on this machine, the outcomes may be completely different. So what really matters is what is statistically, so if you do 10,000 experiments of the same kind, what are the branching ratios of different outcomes, for example. The other thing that is important, so you need to keep doing it, right? So one encounter will harden the binary a little bit. It may or may not be sufficiently hard to merge. So you need to keep doing it. And the rate of such encounter depends on something called n sigma v. So in tutorials, we will explore these kind of rate calculations. So n is the number density. Sigma is some measure of cross-section. So it's dimension of area. And v is relative velocity between the two things that are interacting with each other. So in total, you can convince yourself this is dimension of 1 over time. For binaries, this is same major axis square. For single stars, it's radius square, roughly. tutorial. Okay. So in any case, so you need to somehow increase rate. And if you are particularly interested in black hole binaries, you want all of these happening with black holes only. So you need large numbers of black holes in one place. And as I said, you need high enough densities for it to happen over and over again. And the most natural environment for all of these to happen is dense star clusters. These can be globular clusters, nuclear clusters, young superstar clusters in colliding galaxies like Antony. So several things go in favor of star clusters. They are born with large number of stars. That means they form large number of black holes. They are high density, and their evolution goes in a way that they can aggregate all black holes to the center. So let's look at the properties a little bit. Typically, they are today 10 to the 5 solar mass. That means they were at least 5 times more massive at birth. Actually, 10 times more massive at birth. They are typically old globular clusters, but there are other massive dense clusters in other galaxies. And old also means metallicity low. So what are the physical processes that make globular clusters particularly interesting? Two-body relaxation. We will have a formal description of what two-body relaxation is in later lectures. Essentially, stars gravitationally influencing each other. A natural outcome is a more massive star loses energy, sinks deeper into the potential. As it sinks deeper, it speeds up, so it can lose more energy. Okay? So essentially, if you imagine that there is a central part that is moving faster, because it's a gravitationally bound system, and outside that is moving slower, and velocity squared is roughly energy, which is kT. So you can imagine that this is a thermodynamic system. Inner part has a temperature, outer part has another temperature. Inner part is hotter than the outer part. So energy flows inside to outside. As energy flows inside to outside, because of negative heat capacity, even more energy flows from inside to outside. And this is the runaway process. So if you have a distribution of stellar masses in a cluster, so you have stars mixed with black holes. Black holes are more massive than stars, so all black holes will sink to the center. So this is a small region, very high density, almost exclusively with black holes. These are some relevant time scales. So relaxation time, I will talk more about it tomorrow. Crossing time is how long it takes for a star to cross from that end to the other end. Relaxation time is how long does it take for a star's orbit to forget its initial orbit. I will explain what it means. And for globular clusters, this is what the typical values are. So roughly 1 billion years. The age is about 10 billion years. So all globular clusters are relaxed. And then another interesting timescale is the mass segregation timescale. That is typically the ratio of the average mass of the neighborhood stars divided by the mass of the species that you are interested in times the relaxation time. So for black holes, so this is roughly 0.5 solar mass. This is roughly 10. So this is about order 1/10 or smaller compared to relaxation time. So black holes sink, do stuff, go out. Sink, do stuff, go out. Not necessarily black holes. You can create, if you create, everything is a black hole if it's more massive than a black hole. Yes, so the way it works is the most massive black holes sink first, then the next, and so on.
So why would the black holes, I mean, I understand that they'll sink to the core, they'll try to sink to the core, but why they would again try to go out?
By this. So when the density is high enough, these kind of interactions happen often enough, and each of these encounters get recoils, give recoils to both the binary and the single. If the recoil is large enough, then you can eject black holes from the cluster, which essentially means you are removing gravitational potential energy, which essentially means you are injecting energy to the center. Also, I have, you can, actually this is very, so it's slightly bigger. The one that is going out is slightly shrunk. And this is an example of an exchange encounter. I'm hoping that in the tutorial you will see many such examples of exchange encounters. So the two stars that came in and interacted with the blue star kicked out one of the red stars from the binary and inserted itself into the binary. This happens all the time. In addition to these, in star clusters, you need to take into account single and binary stellar evolution and tidal shocks from the galaxy. This is not directly relevant to today's story, but that's for completeness. These are all the physical processes you need to take care about. Another thing that's very interesting, and this is the story where I will stop after telling you the story. So the real question is, so what I have told you so far is globular clusters form a large number of black holes. Globular clusters collect the black holes, do stuff with them, and then the strong encounters can, in principle, eject the black holes. The question is, how long does it take for this to happen? And as I showed you, that it takes very little time with respect to the overall age of globular clusters. So back in the 60s, Spitzer argued that since it takes so little time for black holes to come to the center and eject themselves, today's globular clusters won't have any black holes left. Because, let's say that you have n stars in the globular cluster. So you have 10 to the minus 3n black holes. They all go to the center. They decoupled dynamically from the rest of the cluster. So in principle, you can imagine that this black hole subcluster is a different cluster. Now let's look at this relationship. So it's a tiny place with very high velocity dispersion. So T cross is very short. N is 10 to the minus 3 times the cluster's n. So this is very small. So that means the relaxation time is very small. Density is very high. So if you do n sigma v, then the interaction rates are very high. So everything becomes super speed in the black hole subcluster. And his argument was, since it's a non-reversible process, all black holes would evaporate within about 1 billion years after the star cluster forms. So today's globular clusters will not have significant numbers of black holes, maybe 1 or 2 left. That's the one that did all the ejecting. Okay. This is wrong. Spitzer was wrong. And tomorrow I will pick up why he was wrong. Any other questions? It created a bunch of high mass stars that evolved and became black holes. A few million years.
Sir, I have a couple of questions. Like,
One second. So, how high mass stars evolve and evolve up to supernova is actually a very interesting physics, and it is not bound by the actual hydrogen burning, etc. So it's bound by, so they burn their hydrogen at such a high rate, and their wind mass loss rate is so high that a lot of this is radiation physics. So independent of mass, for high mass stars, everything goes supernova roughly around 3 million years later. So all of that, all of the black hole formation, neutron star formation, heavy white dwarf formation, everything happens within a few million years. So white dwarfs maybe 10-ish million years. Everywhere. It's a star property, it's not a cluster property.
so you showed that inside the globular clusters, the black holes will first sink and then they will collide with other black holes, and it will try to knock out them. They will go outwards and then again come back. The chaotic trajectory you showed. So for that to happen, we need to have multiple black holes. A single black hole in the globular cluster, if it collides with other stars, I mean, it cannot happen, right? Because it's much more mass.
Clusters typically are born with a few million stars. So typically a globular cluster produces few thousand black holes.
And next is, there will be a collapse time of the globular cluster. So the collapse time is, what is the order of the collapse time compared to the merger time scale of the black holes? Is it much larger or?
It depends on the orbit of the black hole. No one really knows. We know what is needed. Somehow a really massive molecular cloud needs to be compressed very rapidly, so that throughout the molecular cloud there are clumps that becomes Jeans unstable and create stars in one burst. It's very clear that in the Milky Way, the conditions are not conducive to create globular clusters today. But we see formation of globular cluster progenitor-like things in all interacting galaxies. So M51, Antony, there are several different examples. There are some young star clusters that formed in the Magellanic Clouds. They have wide ranges in metallicities and ages. So I think it's reasonable to believe that somehow big amount of gas needs to be compressed abruptly. That's the reason. That's what you need. All right.